Log on, tune in, find out. Another good idea from Cambridge.
Right, so it's a great pleasure to introduce the final speaker this morning, Losev, who will speak about one-dimensional representations of W-algebras.
Thank you, Michael. Well, I will start by thanking the organizers who invited me here to this beautiful place. And so I want to mention that this is my fifth talk on W-algebras in this very room. So I also thank the organizers for their remarkable patience. I'm going to talk about one-dimensional representations of W-algebras. And I will start with a reminder. And here, unlike in Victor Katz's talk, when I say W-algebra, I mean finite W-algebra. This is not a fancy vertex algebra. This is a usual associative algebra. Then I will explain what happens for classical G. And finally, I want to talk about exceptional. And now let me fix some notation. So G, of course, is semi-simple Lie algebra over C. Then I want to consider an algebraic group with this Lie algebra. The universal enveloping algebra of G, which I will denote by curly U. I hope this is curly enough. Then I will need nilpotent orbit O in G and finally I want to fix an nilpotent element from this orbit. Okay. So what I can do with this nilpotent element, I can take an SL2 triple containing it, E, H, F in the usual notation, and then I can define a remarkable affine subspace in G called the Losev slice. This is E plus kernel of ADF. Its main feature is that it's transversal to the orbit. Now I want to consider the algebra of functions on this slice, C of S, polynomial functions. And it is known that there is a nice grading on this algebra by non-negative integers. I will not define it. So we have a graded algebra. Thus we can talk about quantizations. So we are interested in what is called W-algebra. Curly W is associative algebra filtered such that its associated graded is the algebra of functions on the Losev slice. Now, of course, this is not a definition. You have multiple choices of such algebras W. Let me tell you informal defining property. So defining property is that, in a sense, this W is transversal to O in U. The problem with this phrase is that it makes no sense. We are dealing with non-commutative algebra. There is no notion of transversality. So let me give a more formal description. So what I want to do, I want to work in a formal neighborhood of my point E here. However, for non-commutative algebras, there is no notion of completion, like, in the commutative case. So I do a little trick. I will do what is called homogenization. So want completions. Then I need homogenization. And by this I mean the following. Let me start with the Lie algebra. So I form the algebra G sub h bar. H bar here is a formal variable. And by definition, this is a tensor product of G with algebra of polynomials. So this is the Lie algebra over this ring. And a bracket will be given by xy sub h bar is h bar xy. Now I can form a homogeneous version of the universal enveloping algebra U sub h, which is just the enveloping algebra of my Lie algebra G sub h over, of course, polynomial rings. And this algebra really should be considered as algebra of polynomials on G, well, and in additional variable h bar. But now we need to consider a modified product here. Say star. And why I need this modified product now? Well, remember I promised to be formal. I want to consider formal power series. UH wedge, which will be, well, formal power series in all variables I have. Let me write it like this in order to save, 4 square brackets. And this algebra is, and the origin here is E. So I consider formal power series in a neighborhood of E. Now the point is that this star extends to this algebra. That's, just a formal exercise. Now I have this algebra of formal power series with a non-commutative product. And what I want to do, I want to decompose it into two factors. Decomposition. Well, on the classical level, we have the following decomposition. We can take the tangent space to G at E, and it decomposes into the sum of two tangent spaces to the orbit O and to the slice. Now, the point is that this gadget is symplectic. And so, what I want to do, I want to sort of lift this decomposition to the quantum level. I can do this because of this space is symplectic. So on quantum level, I have the following. I have my completed algebra UH wedge, and this decomposes into the completed tensor product of the following gadgets. I will explain notation in a moment. So bold A sub h wedge completed tensor product over formal power series in h bar, and fancy algebra looking like this. Now, what is this? This is formal Weil algebra. And as a vector space, this is the space of all formal power series. This should be C here, I believe. Well, K will be C. Anyway. So this formal power series on the tangent space to the orbit, and H. And again, this is like this is a space, and the product is modified. It's not the usual commutative product. And with the star product. There is a Mayal-Weil formula. You can write this down explicitly. A similar algebra appeared yesterday in Sasha Premet's talk. Now, what is this? This is sort of slice part. The slice part looks like algebra of formal series on S. And again, with a modified product. That's what I mean by decomposition. Now I have this algebra, which is algebra of all formal power series. And I want to consider its subspace consisting of polynomials. So I want W sub h is the space of all polynomials. And the point is that this space is a subalgebra. And this is because of grading considerations. I will not give details. And what remains to do is to return from the homogeneous version to the usual version. And this is done by taking quotient by h bar minus 1. Well, that's a construction. Well, sort of construction. And now let me try to speculate on why this algebra can be interesting. Well, from my point of view, it's interesting because it is closely related to the universal enveloping algebra. So there is a relation, or probably I should say relations, between W and U. One of manifestations of this relation is that we have maps between sets of ideals. Namely, I want to consider the set of two-sided ideals in U. I will denote it in this way. And two-sided ideals in W. I will denote this map by a subscript dagger, like this. And I also have map in the other direction. I have a map between from ideals of W to ideals of U. And I will denote this map by upper dagger, like this. Let me explain how to define this. Definition of J lower dagger. Well, I'm going first explain what's going on the classical level, on the commutative level. Well, on the commutative level, a counterpart of this gadget is a G invariant ideal in S of G. So we have straight J G stable ideal in symmetric algebra. And of course, I can form the corresponding scheme, subscheme in G. I will denote it by V of G, of J, sorry, in G. Then what I can do, I can intersect this with the Losev slice. And finally take the corresponding ideal. That's what happens on the classical level. Let me now explain the quantum construction, which is based on this decomposition. So on the quantum level, we start with ideal curly J. Then we can do homogenization and construct an ideal J sub H bar in UH bar. This is homogenization. This will be a homogeneous ideal, a graded ideal. Now we can take its completion in the topology of formal power series ring. Get something like this. And now, due to this decomposition, here, our ideal also decomposes. We have J overlined sub H bar equal to completed tensor product of the Weil algebra and some ideal in the slice part, I wedge sub H. Now we take this ideal, which lives in here, and intersect it with polynomials. And finally, mod out by H bar minus 1. That's the way to do this. And if you want the map in the inverse direction, you can invert the procedure. Okay. And to finish the reminder, I want to recall one property of this map from ideals in W to ideals in U. Well, the property is that if codimension of this ideal I is finite, then the associated variety of the corresponding ideal in the universal enveloping is the closure of the orbiting consideration. This is associated variety. So I have finished a reminder. And now there is a small gap here, which will be a conjecture I'm going to consider. Oops. So the conjecture is due to Premet. I believe 2005. And the conjecture is really simple. What we claim is that for all G and E, there is one-dimensional module for this W algebra. Following one очередник, I would say, perhaps, what can be simpler than this? Let me indicate two applications of this conjecture. Well, first application is to what is called completely prime primitive ideals. Well, let me recall that an ideal is called completely prime if the corresponding quotient has no zero divisors. Now, how can this stuff be related to this question? Well, in 2007, I proved that if codimension of the ideal I in the W algebra is 1, then the corresponding ideal in the universal enveloping is completely prime. Now, if we know that the Premet conjecture is true, then we can show, then we can answer the following question. I'm not really sure whom I should attribute it. Probably to Joseph. He definitely asked this question on the conference here in March, but the question itself is much older than this, but I believe it's somewhat younger than Joseph himself. So now conjecture 1 implies that there is completely prime J such that the associated variety of J is the closure of O. That's the first application, and the second application is due to Premet. And Premet proved that conjecture 1 implies existence of what is called small representations of modula U of G. This is a question of Humphreys. I'm not going to talk about this, but this is still indication that conjecture can be useful. Okay. No. It is known that this ideal in general will not be unique, unfortunately. For example, a very stupid example you can see, is that if your element is principal, then the algebra is commutative. Okay, now let me proceed to the case of classical algebra G. So here conjecture is true. And I proved this in 2007. And actually, in a sense, more is true. So before I state the theorem, let me specify that G, this algebraic group I mentioned, will be SLN, ON, or SP2N. I allow disconnected groups. Now theorem. Is that there exists an ideal J in U such that associated graded of U over J is the algebra of functions on the closure of the orbit. How is it related to our conjecture? Well, you simply take ideal J lower dagger, and it has codimension 1. It somehow follows from this picture on the classical level. Morally, taking this lower dagger is just to intersect. How to prove the theorem? Well, we want to quantize this algebra, or, so to say, this algebraic variety, closure of O. So what we need to do, we need somehow represent it in the form which will be easy to quantize. And we are lucky enough, this is known. This form is known. This is due to Kraft and Procesi. I don't remember the year. But they, among all other things, represented this orbit closure as a Hamiltonian reduction. I will explain what this means. This means the following. Well, it's not definition of Hamiltonian reduction, it's description of their result. So there is reductive group G tilde and symplectic G tilde times G module V tilde, which enjoy two nice properties. Before describing these properties, I will introduce some notation. So I want omega be symplectic form on this space V, and I want two comoment maps. I want H tilde sub psi. This is a comoment map for G tilde. It's given by the formula, well, if you want to evaluate it at point V, this will be 1/2 omega psi V and V. And similarly, I can define the other comoment map, H sub eta. Here psi is in G tilde, and eta is in G. Now, with this notation, I can state the properties. So properties. First of all, I want to consider the set of common zeros of these comoment maps. So if I want the subvariety V such that H tilde psi V is 0 for all psi, and its codimension is as large as possible. That's the claim. Codimension in V of this subvariety is dimension of G tilde. Which V tilde? Sorry. Oh, so yeah. Yeah, thank you. No, this property is of course not automatic, but their construction implies this property. That's not an arbitrary group and not arbitrary module. Now, so what I can do, I can form the classical Hamiltonian reduction perhaps I need another blackboard. So by definition, it's the following algebra. A I take the quotient of the algebra of functions on V by the ideal generated by these gadgets. And then I take invariance with respect to G tilde. That's the classical Hamiltonian reduction. Now, this reduction comes equipped with a map from S of G. So eta goes to H sub eta gives rise to a map from S of G to this A. On the other hand, I have a map from this algebra to the algebra of functions on the closure of the nilpotent orbit. And now the property B I need states that this map is an isomorphism. It states that we have a map here, and this map is an isomorphism. So this is what I mean when I told you that this variety closure of O can be constructed using Hamiltonian reduction. Now we want to quantize the picture. And if you want to quantize Hamiltonian reduction, that's a general recipe for this. And it tells you that you need to quantize all ingredients of the reduction. That is to replace all classical objects here by their quantum counterparts. And then, under favorable conditions, you are done. So what I want to do now is I want to quantize. So I define curly A is as the straight A, but C of V, the Poisson algebra, is replaced now I have two A's, and perhaps I should have the third one. And the third one will be Weyl algebra, this bold-faced A. That's the now completely the same algebra as considered by Primet. Somehow I also need to replace classical comoment map by the quantum comoment map, but they are the same as functions. Let me remind you that this algebra can be considered as this vector space with the modified product. And, well, I don't have 3 A's, I have 4 A's. So what we know, fact, actually, condition A implies what is called quantization commutes with reduction theorem. And in our setting, this means that associated graded algebra of curly A is a straight A. Now, condition B implies that the natural map from U to curly A, which is obtained in the same way as the classical map above, is surjective. And now A and B together imply that the ideal J, which is kernel of this map, is what we want. That's the ideal we are trying to construct. Any questions?
Is this a primitive ideal?
Of course. It's completely prime. Well, actually,
Yeah.
this algebra has no zero divisors.
And to which cell does it belong?
I believe that's a very difficult question. I was told by Peter Trapper that he tried to understand this with Barbash, and they didn't find a proof yet. But the question is, it's not always integral. It will be 1/2 something, most likely. And I mean, they have a conjecture that for special elements, this corresponds to this Barbash-Vaughan highest weight. Okay, so this was a classical case. And now let me proceed to the exceptional case. Well, the answer in the sessional case looks as follows. G2, F4, E6, and E7 conjecture holds. And E8 is, alas, unknown at the moment at least. Now, let me do some arithmetics. Well, of course, arithmetics doesn't mean number theory. I will just do arithmetics. I will do subtraction. So we sort of have something like, I believe, approximately 150 non-zero nilpotent orbits in all these 5 algebras. Well, of course, one solution you can you can think about, you can hire 150 graduate students, and, you know, well,
You would need 149.
well, I mean, that's not, I mean, this are non-zero. Well, anyway, some of them are really easy, some of them are really difficult. Anyway. So we need to do some reductions. And some subtractions. And now first subtraction is due to Premet. He subtracted something like, I would say, roughly 110. And this 110 are non-rigid important elements. It's not important to know what rigid or non-rigid means. Just, we can reduce our case by case and save our graduate students. Well, so somehow what Premet proves is that Lustig-Spaltenstein induction preserves condition of having one-dimensional module. And here, the techniques he used is here. This is Premet. And techniques using modular representation theory. Now we sort of have 40 elements. And let's continue reducing this. Premet in 2005 subtracted 5 elements from here. And these are minimal nilpotent elements. And a technique he used analysis, of course not mathematical analysis, but analysis of generators and relations. The point here is that relations in this algebra are quite simple and can be, and you can do everything by hand. Now, in the general case, relations are much more difficult. I need to write that this is somewhat like 35. Now, the next subtraction is something like minus 17. And this is due to, so these are elements in G2, F4, E6, and E7. And this is due to Goodwin, Rorley, and Abley in 2009. Well, at this point, one graduate student gets involved, but it's much more economical than my original program. So what they do the same. But they use gap to analyze the relation. So what we have roughly 17 nilpotent elements, and these are nilpotent elements in E8.
What is it, graph? What is it, graph?
Gap. You know, there is gap which is a gap, and there is gap which is computer program. Well, they used the second one. Hopefully. This is 8. And now, let me explain my own contribution to this subject. I managed to subtract 1. I'm not going to compute the result. So this is... And the technique used is Brandon, Goodwin, Klishov, highest weight theory. So this one doesn't look very impressive, I understand. But anyway, let me explain what was done. So I have a certain condition on an important element. So under condition star, which I will write below, so what I found is, well, this will be a complicated phrasing, but I found certain condition now on the highest weight for the universal enveloping algebra. With the following property. The property is that two sets coincide. The first set is a set of primitive ideals, I lambda, with this highest weight, where lambda satisfies condition. This is primitive ideal corresponding to lambda. And now this is precisely the set of ideals which you produce from one codimensional ideals in W. In particular, if you found a highest weight satisfying this condition, whatever it is, you solve the problem. And now this one means explicit computation of this highest weight. And it was done, I believe it was E8, A5 plus A1, something like this. This is one of the biggest rigid nilpotent elements in E8. Now, what I want to tell you is what condition star is, and somehow clarify the nature of this condition here. So star is that if you take reductive part of the centralizer of E of our nilpotent, then it's semi-simple. Very strange condition. And now a miracle happens. The miracle is that this condition, for whatever reason, is satisfied by all rigid elements. This result is purely experimental. You have a description of rigid elements in classical algebras, this combinatorial description, and you have tables for exceptional algebras. You check everything, and this holds. This is about this star. And now, what are conditions on lambda? Well, the conditions are sort of combinatorial. And here, well, this is I should say, beautiful and very impressive theory of primitive ideals in universal enveloping algebras. In particular, what we need to check, well, this condition is union of four subconditions. And the most implicit one is that associated variety of this ideal I lambda should be the closure of our orbit. We cannot escape it because we are in all our ideals should correspond to the given orbit. And this one is very difficult to check. Well, you can simplify it a little bit, but anyway, it's difficult. Okay. Now, some conclusion. Let me explain why I...
If it is semi-simple, you can more or less effectively introduce generators. What is the purpose of assuming that it's semi-simple?
What is semi-simple?
Semi-simplicity, star condition. What is the real purpose, technical or whatever purpose? That you can introduce generators and...
No. Right? This representation theoretic stuff. Let me explain.
How it reveals itself?
Let me explain you. We all know that if we take a semi-simple Lie algebra and we have a one-dimensional representation, then this representation is trivial.
Yeah, but there is W, we need to translate it to the level.
Right, you are right. Now, if you take this reductive part, it sits inside W. You can show this. And now, you know, this highest weight theory of Brandon, Goodwin, and Kleshev has something to do with this subalgebra. That's the point. Okay. Let me conclude by explaining why I like this -1 here. Well, first of all, there is hope that this -1 can be converted to -17. Maybe with some gaps, some graduate students, stuff like this. Another reason is the following. Somehow, the point of W-algebras is that they should clarify issues with universal enveloping algebras. It's somehow a big goal. Now, so far, it worked exactly in the opposite direction. You used results about universal enveloping algebras to get some results about W-algebras. Or in some cases, you do W-algebras to get results about W-algebras. Now, this result, this equality here, is different. You have something about a universal enveloping algebra. You can describe highest weights of some nice primitive ideals. In particular, all these ideals are completely prime. And you can do this in a very important case of rigid elements. In a sense, it's somehow most complicated case. And I don't know any proof of this result. I cannot imagine a proof which will not use W-algebras, because you need to say that you have some finite dimensional representations, and you can analyze it using this semi-simple subalgebra, and you are done. So, summarizing, this is a result which tells you something about universal enveloping algebras using W-algebras. I have finished.
How many from 150 satisfy this star condition?
Oh, Vanya, I don't know, sorry.
Many,
I didn't
some,
count.
no,
That's a typical condition for exceptional algebras.
typical condition, yeah.
Could I hope something that if they are on the right board on the left is written codimension of E and W is say some other number, that this other number should have a report describe the Goldie rank of
It gives you.
lambda.
It describes what is called multiplicity. It's related to Goldie rank.
So one reason to, it's related to what Wolfgang said, one reason to have completely prime primitive ideals was to find the scale factor in Goldie rank. Is this, now, do you know how to do this now for classical?
Well, first of all, I haven't found all this highest weight with these conditions. If they were found, I don't know. So somehow Joseph puts it like this: if you have enough completely prime primitive ideals, then you can compute everything. Well, another point here is that all these ideals are completely prime, but it is not known whether a completely prime ideal comes from here, and more likely it is not true. Maybe it's true in type A. That's open question.
A small remark about this element 5 plus R1. In case E8 exists two important with type R5 plus R1. One of them is even, and for this reason all is okay, but other is rigid. And if notation of thinking, I think that is R5 plus R1 is one street.
Well, maybe.
For each W-algebra, for that W-algebra, how many one-dimensional irreducible representations?
I believe that in this work
So far it's a
they found the numbers.
lot.
As far as I remember, it is 1 or 2, right, Gilbert? But somehow, well, if you have rigid element, then the number is finite. If it's not rigid, then the number is infinite.
My second question is, how many graduate students do we need to support?
Oh, I understand. Yeah, that's a professional question. I don't know. So this guy is English, so I mean, you don't need to support him. You cannot, I believe.
Other questions? Can you explain how you use this Brandengood clash of highest weight theory in your calculations?
So somehow, as I answered to Vanya Cherednik, what happens is that you have this semi-simple subalgebra in W. Let me write it. My favorite notation is Q for this. Now, highest weight theory, somehow there are different notions of highest weight in this theory. But one of the notions is related to the Cartan subalgebra here. You have weight decomposition according to Cartan subalgebra, and somehow the highest weight is what you need. Now somehow we know, well, I mean, so somehow in their theory, highest weight, highest weight to consider is a representation of smaller W-algebra. And somehow this W-algebra consists of two parts. One of these is Cartan here. Now what you know, if you know that this action is trivial, you know that your highest weight, the component of highest weight is 0. And this condition can be translated to the universal enveloping algebra level. And somehow vice versa.
Other questions, comments? Okay, then let's thank the speaker again.